Okay, so I'll promise you kind of minimal math during this review session. So I just want to cover some of the key concepts and intuition for like, all the stuff. There's a lot of material. Chiwei goes through a lot. I don't know how he does it. So I'm gonna try to get as much as I can covered, but might not get everything covered. Um, and uh, I took this class with Jalali, so not all the material is the same. So some of this is kind of new to me too. So we can I'll discuss this together. And there's gonna be hard cutoff at 7 p.m. because I do have to go then. But I'll be available for questions on Discord, and I might polish up the slides a little bit tomorrow morning. Yeah. So a couple tips and tricks for the exam is word on the street is that wait, is your exam open book, by the way?
Apparently not. Apparently just cheat sheets.
Oh, cheat sheets. Let me go back a sec. Okay. How much cheat sheets do you guys get?
I think you said 3 pages.
One full page.
Oh, is it?
Oh, it's one full page for the midterm, but 3 for the final.
Like, all right. Yeah, that's useful information for me to know. Yeah, but like the cheat sheet, basically you want to put all the equations you can on that thing, and then like minus the equations that you already like memorized or know, like Maxwell's equations, maybe you've memorized that. Because I know that Chiwei's exams tend to be more equation heavy. Don't panic. A lot of you guys are very, very smart individuals. If you guys just follow your gut, you guys will probably get the right answer. And stuff that if you've taken 101B or 163A, there's like some concepts that also might pop up in on your exam or in this class, I guess. So I guess the first thing, when I went through you guys' textbook, I noticed a lot of tensor notation. So are you guys comfortable with tensors?
Is a tensor just a matrix?
Basically,
Kind of.
yeah. So yeah, tensor is basically a matrix. You might encounter something called Einstein notation. So we have this A mu B mu, so one's up and one's down, and you just sum all the indices. And then you might see something like this. So you take the news here, the common news, and you sum them together, right? So it takes a vector b with the new coordinates to a vector b in the new in the mu coordinates. Yeah, and then yeah, they're basically matrices. At least rank 2 tensors are. Rank 3 tensors are like an m by n array kind of. We kind of think of it in like computer science terms. And etc. I think the book uses order 3 and order 2 sometimes for rank. But yeah. And then all tensors sum by Einstein notation. And yeah, so basically the indexing, it's kind of like a linear transformation. You kind of think of it like that. And I asked a question, how would you write change of basis in tensor notation? So it's kind of like equation 12.115 here. You can kind of see it. So you have this matrix here going to this matrix here. And like this is like your change of basis, like matrices, right? Like the S and S inverse, right? So yeah. So yeah. By the way, pause if you have any questions. Feel free to interrupt me. Yeah. So was the tensor stuff all clear?
Yeah, it's pretty good so far.
Okay. So chapter 1.1, so they talk about like the photon nature of light. So you might have encountered this in some of your other classes too. And the theoretical foundation for the photon being both a particle and a wave comes from de Broglie's hypothesis, where they basically state that everything is both a particle, everything that has like a particle-like structure has like a momentum and like frequency, right? Like, and then the experimental foundation is, you have Young's double slit experiment where the light goes in and you get this interference pattern, right? And this interference pattern can only happen if light's a wave. And you also have a particle-like nature, where it's the experimental foundation for that is the photoelectric effect or Compton scattering. If light was a wave, then it wouldn't be able to kick out metal atoms, and it wouldn't be able to scatter, right? Compton scattering, what it is you take particle A and then you take particle B. Particle A hits particle B. If light was a wave, then it won't be able to hit the particle and you won't be able to see the second particle scattering, which Compton scattering, the second particle is an electron, actually. So yeah, that's the questions down here. I guess, are there any questions about this? All right, moving on. So, and then your second chapter, we get to talk about some, some Maxwell's equations, optical fields. So we talk about the D field and the H field. So they're kind of like E and B fields inside of materials. So yeah, so basically the magnetic and electric field, they make dipoles. So you get the P vector and the M vector. So why you have a plus sign for the polarization vector is because the plus attracts the negative charge. And so you add it together to get the D field. And Lenz's law makes the induced magnetic field go the opposite way. So you have a negative sign for the magnetization. And normally the magnetization is negligible in optical frequencies. And this is because if you kind of visualize what happens is that if you have a wave and it's traveling at high frequency, it kind of makes the magnetization spins of the particles move around more randomly, versus if it's like, if the wave is more like DC, if it's like, if you have like a straight magnetic field, right? If it's not like a wave, then what happens is that all of the magnetic domains, like all of the arrow thingies, they all line up in the same way. Yeah. And then to talk about Maxwell's equations and conservation of charge. And then there's polar and axial vectors. So a polar vector is basically an ordinary vector like position, velocity, or electric field. And an axial vector is basically the cross product of two polar vectors. So angular momentum is an example of an axial vector, like R cross V. Magnetic field is also an axial vector, because if you think back to Biot-Savart law, you have the integral of some differential position crossed with like something else, right? And then there's certain symmetries that I guess are important. So electricity, you swap sign with space, but like in time, if you like flip the time, it stays the same. Magnetic field, if you like make the time negative, then it'll swap the sign, but with space, it'll stay the same. Intuition basically comes from the Lorentz force law. So if you think about how acceleration might transform when you flip space, right? And you make positive x, negative x. Acceleration will stay the same. And so you see this E here is directly proportional to the acceleration. And so it will transform with the acceleration, versus this magnetic force thing. it'll transform with this velocity. So because the acceleration will keep its sign when it like with space, but it'll change its sign with time. Yeah, so and then think about some boundary conditions. Shoot, let me yeah, so what happens at the edge of the conductor? Boundary conditions are very important for like waveguides and stuff. We'll talk about that a little later. So are there any questions about what was just discussed? All right. There are no questions. Let me keep moving on. How to get the power of an electromagnetic wave? So anytime you see power or intensity in this class, it's you normally just take like so I guess for an EM wave in particular, it's you first consider energy density, right? It's the energy density of the E field plus the energy density of the magnetic field. And you can derive this formula by thinking about how energy is stored in inductors and capacitors. Basically, you want to find E dot J because if you do the dimensional analysis, the units just work out, so you get power. And basically, to get the power of an EM wave, you kind of want to think about the power flowing in minus the power flowing out. So the pointing vector is the power flow, right? It points in the direction of power flow of an EM wave. And so when you so when you find the power of an EM wave, you basically take the energy density flowing out, right? Plus, and then you add the divergence of the pointing vector. So that gives you so that gives you like the divergence of the pointing vector is energy flowing in, and then minus the energy density is the energy flowing out. And then the last term you might see in the textbook, you might have some dipoles in the material, so you also have to consider the energy there as well. Any questions? Okay. I guess they're in all waves obey an equation called like the wave equation basically. Basically what it is the second derivative with respect to position equals 1 over the speed of the wave squared times the second derivative with respect to time of the wave. And this is useful just to derive the speed of light. And you can just, play around with Maxwell's equations and you can get this wave equation. So for harmonic fields, yeah, so basically the solution to the wave equation is complex exponentials, which are basically waves, right? That's why it's called the wave equation. And the time average of the pointing vector gives the light intensity or average power density. And this is just basically from the definition of the pointing vector. And you can relate polarization and magnetization to the E and B field by the convolution integral, because basically you can kind of think about it like you take each point in the material, and the E field will cause an effect, right, in that point in the material. And then from that effect, you need to also sum up all the other effects elsewhere in the material. So and that sum you carry out by basically doing a convolution integral. And you can calculate easier in the Fourier domain. So are there any questions about this? If you guys want me to show, I guess like pictures and stuff, I can always like exit out of the slides and just, you know, show some images. You know, just go on Google Images and search up some relevant images. All right. So, and then the next part is talk about polarization. So how do EM fields propagate? So we know in free space, the electromagnetic waves are transverse, meaning so they might travel in the z direction, but they will like you'll see the E field, it'll go like up and down in the x direction, and then you might see like the B field go up and down in the y direction, and then they'll move together in the z direction. That's what basic transverse means. And yeah, so we can rely on solely the E field when we consider polarization because of this fact normally. So the shape of the polarization, a lot of this intuition just comes from, you know, if you have a circle, it'll be described by the a squared plus b squared equals r squared equation, right? If you have an ellipse, it'll be a squared over, you know, x squared plus b squared over y squared equals 1, right? And yeah, so in general, we have different phase and amplitude for the two components. So we get an ellipse. And the special cases are circular polarization, where we have the same magnitude for both x and y. That's kind of like this r squared term, right? And then we have a phase difference of pi over 2. And linear is just when we have the same phase, where everything can just cancel out. And, you know, we like linear, you kind of visualize it as like, you know, up and down polarization, right? Or like side to side polarization. And like a fun fact is that, you know, if you have a phone, it's like it polarizes light in a certain way. So if you wear sunglasses and like you tilt your head a certain way, then you actually can't see, your phone will be like completely black because of the way that the sunglasses and the phone are like polarized together. So like if you have like a polarization thing where it polarizes like up and down, and then another thing with polarization side to side, you can't see anything if light goes through the first one and the second one, basically, which is kind of interesting. That has to do with like linear polarization. Circular is like you kind of see the wave like go in a circle, and the ellipse is like the ellipse, you know, will travel around and like trace out an ellipse. So this chapter basically just gives you the general form for the electromagnetic wave. Yeah, it's not too exciting. So yeah, I guess I kind of went through like, I guess my thoughts and intuitions for chapter 1. Do you want me to clarify anything?
Actually, I had a quick question about the 2 slides ago. Yeah, right there. So you were talking about how the E and B waves are essentially transverse to the direction of motion.
Yes.
And once we start getting into waveguides, they start introducing an additional longitudinal component to the E and B fields in terms of the TE modes, TE, TM, and TEM modes, and even the hybrid ones. And that's where I can kind of deal with the math, but the intuition is just sort of not there. So what exactly does that longitudinal component add to the wave propagation? Is it like altering speeds as it changes along the Z direction?
Let me skip to that slide real quick and answer your question. Okay, so basically for chapter 3, I guess your exam is tomorrow, so probably don't do this. Don't read Griffith's chapter 9. Just copy the equations down, but that you see in Lou's book. But basically, how waveguides work, to answer your question. So in free space, ENM waves are fully transverse, but if you have like a hollow metal tube, and you have like a wave, electromagnetic wave in there, right? You have certain boundary conditions where like at the boundary, right, you'll have like metal, a perfect conductor, or like a really, really good conductor, right? So what happens there is that on the surface of a conductor, all the voltages have to be the same, right? And basically, if we have an EM wave, let's say we have like for the sake of contradiction, we stick an EM wave inside a hollow metal tube. If we assume that we have transverse electric and transverse magnetic, then by Gauss's law, we get this equation. And by Faraday's law, we get this equation down here, right? So we get an E field with zero divergence and curl. So we can write it as a potential. The metal surface has to be an equipotential, which if we then use Laplace's equation, the field has to be zero because the field has to be the same throughout. So it's basically a consequence of the boundary conditions inside of a waveguide for why the field can be transverse. Does that make sense?
Yeah, thanks.
Yeah, because in like free space, the field just it does its thing, but in a waveguide, it like hits the surface and then it basically is like, wait a second, I gotta go forward. That's basically what the E field does.
Okay, yeah, thanks.
Yeah. Okay. So the D field is characterized by a convolution integral. So you need to sum up the effects of polarization at all points in space in the material. So that's basically like an integral, right? Like if you have a curve, you take this a bunch of like small like rectangles, right? It's kind of like the same idea. An electric field takes time to propagate, as all information can only travel the speed of light. And so you need a convolution with time there as well, and which means you can just take a Fourier transform if you want to simplify calculations. It's kind of I think a meme in I guess like photonics, like the more physics side of EE. I guess even like the more signal side, where it's like everything's a Fourier transform or a Laplace transform. But yeah, space and time non-locality. So basically cause momentum and frequency dispersion. Basically, the fact you have to take the integral. And the eigenvalues of the Fourier domain, susceptibility, and the epsilon are generally complex. And the index refraction is just the square root of epsilon over epsilon naught. So that just tells you how light and like electromagnetic waves and fields behave in the material. And the real part gives you how much like light bends in the material. So it's like your traditional index of refraction, right? Where like, n can be equal to like 1 point or like is around like 2 in water or whatever. And then, the light goes in and then it bends, right? Or you have a prism, right? And you have white light and, it'll bend all the light, the white light into a rainbow, right? You can model that with the real part of the index of refraction. While the complex part basically gives you the optical gain or loss. So let's say you have a laser, right? And you have a material. So if you have a complex part, which is positive, it'll basically say that the light gets dimmer as it goes through the material. If it's negative, it means that the light gets brighter. And you can kind of see this from so like if you have shoot I can't write. Wish I could. I don't have an iPad. But so it's like exponential like I to the kx plus like wt, right? So k is complex. So it's like a real part of k plus I times imaginary part of k. So you can kind of see it there. oh yeah, the equations are here. So the K is real, and then the imaginary part. And you can see that if K is positive, if you plug it back in here, I times I gives you negative. So then you get like negative Z. So then that means that you lose amplitude as you propagate. And then negative, so negative I times I. So I times I gives you -1, -1 is 1. So you get positive Z. So that means that you get the thing gets brighter as you propagate. So skin depth is 1 over kappa. That's basically so if K is positive, then skin depth is 1 over kappa. That's a distance the wave travels before losing about 67% of its energy, which I guess is useful for a lot of engineering applications. And yeah. Are there any
Okay,
questions?
sorry, quick question.
Yeah.
Are these equations, did you get them from our textbook or from a different book?
No, I got this from Griffiths, chapter 9.
Okay.
Griffiths
Okay,
intro
just want to make
to
sure.
yeah. But I mean, you see similar equations in your textbook actually.
Yeah, they're just a lot more spread out. This one seems to have a bit more condensed.
Yeah. I definitely recommend Griffiths intro to electricity and magnetism if you're struggling to understand parts of the textbook here, because I think the textbook like J.M. Liu wrote isn't very good at introducing you to the material. It like kind of assumes certain background knowledge. Like yeah.
Mhm.
Okay. So this textbook, I guess, and you probably see a lot in class. Like, you see references to isotropic and homogeneous. So I guess to clear some of that up, so isotropic means it's radially symmetric or the same in all directions, and homogeneous means translationally symmetric or the same in all locations. So homogeneous means that if you shift like your x coordinate, like let's say like from like x equals 0 to x equals 5, you still have the same thing going on. So if you see B, this is an example of something that's homogeneous, but it's not isotropic, right? Like if versus isotropic means if you like rotate your system, you'll see the exact same thing. And and I guess there's Noether's theorem that kind of relates to these two. So if the system is isotropic, you need conservation of angular momentum, and homogeny means conservation of linear momentum. But in our case, if the material is isotropic, it means that the susceptibility and the permeability are scalars. What that means is that if you take a point, let's say like x equals 0, you have like effects like right from like that from every point that's like let's say like 1 meter away, right? Well, isotropy means that the effect from every point that's 1 meter away is the same. Meaning that we can just treat x and epsilon as scalars, because in the tensor case, where it's not isotropic, we kind of see that like we kind of see that the first column, right, or the first row basically gives you like how it will affect the polarization for the x component, right? So like let me go to the next slide. So if you see here, like so like if you have isotropic material, the electric field in the x direction will affect the polarization in the x direction. The electric field in the y direction will affect the polarization in the x direction. In that this relationship is by the susceptibility 1, 2, right? In this element in the susceptibility matrix. If it's isotropic, it means that basically that it's the same in all directions, so that you only have like no matter what direction you point your field in, everything will just be the same. So you can treat this entire giant matrix as just a single number, if that makes sense. Yeah, and then
sorry.
Yeah.
Quick question about the tensors.
Yep.
So in the top right corner, you have them diagonalized, and I'm not sure if you might know this, but we have these questions in our homework and in an example midterm that we were given where we were required to find the eigenvalues and eigenvectors. Do you know what order we're supposed to put those in when you diagonalize it?
It doesn't really matter. You can put it in whatever order you want. You just have to put, so basically if you, let's say you have like chi1, right? If you, once you get the eigenvalue chi1, you'll get a corresponding eigenvector to the eigenvalue for chi1, right? If you remember from your linear algebra class, you just take, so you take your matrix A, right, minus lambda I. So you plug in chi1 for your lambda, and then find the kernel of that matrix, right, A minus lambda I. And then the kernel of that matrix, when you plug in chi1 for your lambda, that basically gives you the corresponding eigenvector for chi1. So you should put that eigenvector with chi1, basically, if that makes sense.
Okay.
So like it should go like here in the first entry in the vector.
Okay, thanks.
Yep. Are there any questions? Other questions? All right. Yeah, so we were talking about non-isotropy. That basically means a potential for birefringence, because epsilon is related to n. The permeability, or like epsilon, it basically non-isotropy means that in different directions you have different permeabilities, which means you get different index of refraction, which in different directions, which is a requirement for birefringence. Where you basically have, if you shine light in one direction, it'll bend a certain amount, but if you shine light in a different direction, it'll bend a different amount. And that's the phenomenon known as birefringence, which you need to build wave plates. In order to build a proper wave plate, you need to have a birefringent material. And what is a tensor? Just a matrix or n-dimensional array. I guess if you want some more examples, there's some examples from like special relativity in Griffith's Intro to Electrodynamics, chapter 12. But you don't need to do that right now because you have an exam tomorrow. So it's probably best to just make your formula sheet, do the practice questions you're given, and yeah, get the understanding a little later. Yeah, so interpretation. So chi I1 means effect on E field in the J direction, on P in the I direction, as I explained before. So you can always diagonalize this matrix, so you don't really need to worry about these off-diagonal entries. And I guess there are meanings to these eigenvalues too. So there's a theorem in like linear algebra called like Spectral Theorem, which means that if you have no loss or gain, it corresponds to having like real eigenvalues, because there's no like imaginary component basically. If you don't have an imaginary component, it means you have a purely real index of refraction, which means you don't have any loss or gain. So it also means from like linear algebra that you have a Hermitian symmetry, a matrix with Hermitian symmetry, which means that if you take the conjugate transpose of the matrix, you get the original matrix back. If the ith eigenvalue has a negative imaginary part, it means that you get an optical gain in the ith direction. So let's say you have the x eigenvalue gives you a negative imaginary part, then you get a gain. If it's positive, then you get a loss. That means you lose light, basically. And if it changes polarization of light, it means it's optically active, and you get a non-symmetric matrix. And if it keeps the polarization the same, it's symmetric. So if you're building a wave plate, you want something that's optically active, and so you'll get probably a non-symmetric matrix. And in a magnetic material, it's pretty similar to the non-magnetic material, the meaning of the eigenvalues. Although I guess if it has optical loss of gain, the structure of the matrix is a little different in that it's not symmetric at all, versus in the non-magnetic material, like you don't have the Hermitian symmetry. If you can have optical loss of gain, but it's still symmetric. Any questions about this? Okay. So yeah, this is basically describes birefringence basically. So basically, if you're traveling in the let's say you have a wave, the electric wave is going in the x direction, and the magnetic field is going in the y direction. Then you want your y and your x to be different to exhibit this property of birefringence. So yeah, so like the birefringent axes have to be like, you have to have difference in extra refraction. So I guess the intuition for this chapter, 2.3, is you basically have quantum mechanics. This chapter talks a lot about like population and basically citing one energy state to the next. It talks about like a density matrix. So what is that? Basically, if you study some quantum mechanics, you'll encounter something called Dirac notation. So if you have a state x, you can represent it as a row vector with like the arrow pointing to the let's see, right to the left, and then a column vector is the caret, or the arrow gets pointed to the right, and the left pointing thing is equal to the right pointing thing if you take a complex a conjugate transpose. And the density matrix is just take the outer product of the thing. So you take the row vector m, and you matrix multiply by the column vector n, and m and n are arbitrary basis vectors for the states. And basically what it means is it just gives you the probabilities of being in each state, basically. Like if you have like a initial state, like let's say like 1 0 0 0, like if you have initial state 1, and you matrix multiply the density matrix by the initial state 1, it'll give you the probability of you going to like some other state. So it's kind of like a Markov chain kind of deal. And yeah, so how do you get to the next state in quantum mechanics? So the energy between two states, you have this NF bar and NHF relation. So we need to boost that discrete energy level by using some type of light or energy by the frequency determined by NHF. So for a laser, if you want to excite a bunch of electrons, up to some energy state, so that when they come back down, you get some type of light coming out, right? So you get a photon beamer laser. And how did they derive these equations? Honestly, I don't even know how they derived it. Just put it down on your equation sheet. Yeah. And then chapter 2.4, they kind of expand on effective mass and those ideas from EU2. And basically the conductivity in a material can change with frequency. And the intuition behind that is, different materials might have different capacitances and inductances. And if you remember from your circuits class, right, the frequency response of like different circuits, it'll change depending on the capacitance and inductance in the circuit, right? It's kind of like the same idea with materials. The conductivity will change with the with frequency, because the response will change with frequency, and so the susceptibility and permeability will and because the susceptibility and permeability depend in part on conductivity, susceptibility and permeability might change with frequency. So the plasma frequency is when the boundary condition of the real part of the susceptibility goes to 0. And that frequency is much larger than the plasma frequency. The imaginary part goes, basically it approaches 0. It doesn't, like, it's not equal to 0. And the real part is positive. So the material kind of becomes transparent to this frequency. And our frequency is lower than this, the real part becomes negative. So n is, you know, is positive imaginary. So it becomes kind of mirror-like. So if we go back here to this over here, you can kind of see the equations. So you have K here, the dependent on conductivity, dependent conductivity. Yeah. Okay. And then 2.5, the Kramer-Kronig relations. You have the real and imaginary part of the susceptibility are coupled. This is basically straight mathematics. This, if you take a course in complex analysis, you might get to derive this, the Kramer-Kronig relation. Basically what it says is, if you have a complex wave function, if you have the real part of the wave function, you can get the complex part. You can reconstruct the complex part. Alternatively, if you have solely the complex part, you can reconstruct the real part. And you can kind of see that in both the real and imaginary parts, they're scaled with the same parameters. So in some sense, they're coupled, right? Because if you change one, you'll also change the other because they scale with the same parameters. And then I guess chapter 2.6 talks about some external factors. It's similar to chapter 2.7. And the intuition behind, this chapter is they want to get at is that not all material is linear. So polarization of some material may not scale linearly with electric field. So like some material, if you apply a really strong electric field, the polarization will increase like dramatically. So this chapter, we explore a Taylor series approximation for nonlinear materials. So like there are these fancy names like Packel's and Kerr's effect. So Packel's effect is a third order expansion, and it needs to have a certain type of symmetry to work, called central symmetry. What that is kind of like a starfish symmetry, right? If you imagine a starfish, right? If you have a hexagon here, right? It's central symmetric. So if you cut a line, so all of its lines of symmetry go through the center. That's what central symmetry means. Like a hexagon or a starfish. So, and the Kerr effect is a fourth order expansion, and it's usually kind of small. And the magnetic and electric expansions are pretty similar, where the difference comes from the transformation or symmetry differences that we discussed earlier, where the electric field it doesn't change its sign with I think it was space, and then the other it changes with time, but magnetic field changes with time, but it doesn't change with space, and and then this another part is talks about like deformation, stress strain tensors. Basically, waves can deform things, and by deforming things, you might make certain dipoles in the material closer to a certain point than it would be otherwise. And so you need to consider those effects too with the stress strain of the material. It's kind of like general relativity in that if you have like a planet, it'll curve space-time. So matter tells space how to curve, so space can tell matter how to move. So it's kind of like electric field tells the material how to bend, so that the material can tell you how much it affects the D field, or something like that. Chapter 2.7 is pretty similar to chapter 2.6, and the form of the tensors you see here just depend on the crystal structure. I guess that's all of chapter 2 that I kind of went over. Is there any questions?
Do you happen to know what birefringence and non-birefringence are?
Yes.
Because I thought I heard you mention it, but I didn't see it written down.
Okay. Birefringence is so I wish I could write. So let's say you have a you have ny does not equal nz. Birefringence is if you have a magnetic field going in the y direction and an electric field going in the z direction, and ny does not equal nz. Let's say you have, instead you have ny not equal nz, but x does equal ny. If you have an electric field going in the x direction and a magnetic field going in the y direction, then it's not birefringent with respect to your EM wave, if that makes sense.
Oh, okay, that makes sense.
Yep.
Thank you.
Yep. It basically it means that you'll bend your light differently if if you shine your light in the x direction versus you shine your light in the y direction, it'll bend it differently. That's what it kind of means. Yeah, so waveguides. So waveguides, as we mentioned before, and EM waves are fully transverse in free space. But when you have a material with some conductance, you might get some transverse component. So different modes. TE mode is when the electric field is equal to 0. TM transverse magnetic is when the B field in the traveling directions are equal to 0. And TM only happens, transverse electric and magnetic only happens in dielectric material, where the conductance is smaller. So that's when you have BZ equals 0 and EZ equals 0. And hybrid mode is when both are non-zero. And you can kind of get the equations for the modes by solving this equation 9.181 and using separation of variables to kind of derive the conditions. And the modes are basically standing waves, which is why you see orthogonality. So this chapter, you talk about isotropic mediums. It's kind of review some 1C in that, wavelength decreases by a factor of index refraction, frequency stays the same. I guess the intuition is if you hear a certain pitch, you'll hear a certain note, and that's associated with the frequency. So similarly, if you have a red light going through a prism, if it goes out of the prism, you'll still see the red light. So therefore, the wavelength must decrease because the speed of light is lower in the prism, and the frequency must stay the same because you still see the red light. And yeah, the speed decreases by a factor of the index of refraction. In wave plates, they alter polarization of light via birefringent crystal, and it's dependent on the thickness of crystal, index of refraction, and wavelength of light. Yeah, and there's a lot of different types of wave plates that the book goes over. And then I guess 3.3 explores the Gaussian mode and Gaussian beams. These are just solutions to the Helmholtz equation, or the wave equation. And the Parax approximation basically describes a small angle approximation to the propagation of the beam. That's where you treat. So basically, you might have an x component and let's say like a y component, so that the beam is going like that. Let's say. So you have an angle here. So so basically the Parax approximation was to say that the y component is just equal to this angle here, and the x component would just be equal to the length of the hypotenuse times 1 plus the angle squared over 2. Yeah. And I didn't really get to explore much. I didn't really get to prepare much beyond that. So I guess some idea behind like mode coupling is that each wave mode is kind of like a standing wave, and so each mode is orthogonal. So we can kind of think of like superposition principle when we think about like mode coupling. So yeah, guess it is 6:51. we don't really have time to go through all the book equations I would want to. Yes, are there any questions or confusions about what's been going on in the class so far that I didn't get to?
Yeah, quick question.
Yeah.
So with wave coupling, it's essentially just the power transfer between two waves next to each other, basically.
Yeah, basically. It's like if you have like TE 01 and you transfer power to TE 02. It's basically that.
Okay, sounds good.
Yeah.